Solving nonlinear systems of equations. Nonlinear systems means that we are not looking for where lines cross one another, but where other functions may be crossing one another. We just learned a lot about conics, like parabolas, ellipses, and hyperbolas, as well as straight lines and other functions. What if we want to find out where these types of graphs cross one another? For our first example, we are going to solve this particular system using the substitution method. Just like regular linear equations, as we solve them, we can use substitution method or elimination method, or possibly even a matrix. With nonlinear systems, we cannot use a matrix usually. So this example is going to be x squared minus 3y equals 1. And the graph of x minus y equals 1. Now you'll note that the first graph is actually a parabola and can be rewritten to make it a little bit more clear that it is a parabola. If I solve for y, I'll end up with y equals 1/3 x squared minus 1/3. The second equation is actually a straight line, and it can be rewritten as y equals x minus 1. If you don't immediately see why, you are more than welcome to work it out on your own. Let's take a look and see what the graph looks like. As we're graphing the parabola and the straight line, what we want to be looking for is where do they possibly cross one another. It's possible that the line doesn't cross the parabola anywhere. It's possible it will cross it exactly one time, and it's possible it will cross it 2 times. We will see. You'll note the parabola is crossing at negative 1/3 on the y-axis, and it's crossing the x-axis at plus and minus 1. The line has a y-intercept of negative 1, and it has a slope of positive 1, which means I'm going to rise and run at the exact same rate. Now you can see from my graph, it's very difficult to tell where they cross one another, if at all. So we'll see. Trusting a graph is probably not a great idea, so let's move on to the algebra and see what happens. I'm going to rewrite the first equation. X squared minus 3y equals 1. And I'm going to note from my second equation, the straight line, that y is equal to x minus 1. I'm going to go ahead and draw a line here, and I'm going to dump x minus 1 where y is, giving me x squared minus 3 parentheses x minus 1 equals 1. I'm going to use the distributive property. Now be really careful when you distribute the negative. It has to change both signs to give you a plus 3. And I'm going to notice we end up with a quadratic, which means I have to get the whole equation equal to 0. So I have x squared minus 3x plus 2 equals 0. Now I have a choice here. I can use the quadratic equation, or I could just factor it. Since this one does factor, I'm just going to factor it into x minus 2 times x minus 1 equals 0. Setting each expression equal to 0, and solving each of them, I get that x equals 2 and x equals 1. Now at x equals 2, I need to plug in x equals 2 into an equation. Now I can plug it into the first equation, the parabola, or I can plug it into the second equation, the line. It makes no difference. I end up with y equals 1 regardless. Which gives me the ordered pair, or the point, 2, 1. At the point when x equals 1, again, I can plug in x equals 1 into either equation. Either way, I get that y is equal to 0. So I end up with the point 1, 0. So my graph was a little off, but that's okay. It should have gone out just a little bit further and ended up around there. We'll just make a big dot where it should have been. So the points of intersection are much harder to see with the graph, but algebraically it doesn't matter. We're going to end up with the right answer. The next example, we're going to solve the system, and we'll use substitution again. So these nonlinear graphs look a little different, but the same idea is going to hold. My first equation is y equals the square root of x. My other equation is x squared plus y squared equals 6. This graph is actually a circle centered at the origin with a radius of root 6. Root 6 is about equal to 2.45, which is about 2.5. So what I'm going to do is I'm going to replace the square root of x for y in the equation with the circle, giving me x squared plus x so the root x squared will become x squared plus x plus 6 equals 6, pardon me. Let's take a look at the graph first before we try to solve this. So a radical function, y equals root x, is sort of like a sideways parabola, but we're going to end up with only the top half. Notice y has to be positive and x also must be positive, because we can't take the square root of a negative number when we're doing graphs. There we go with the radical function. The circle, again, is going to have a radius of about 2.5. And we're going to see what the interaction is going to look like. Again, sometimes these are very difficult to graph, so we try to make them as accurate as we can. There we are. Now back to our equation. We have x squared plus x equals 6. I noticed before I move on that I have a quadratic. Usually I get 2 answers from that, but if I look at the graph, it looks like exactly 1 answer. So we'll need to double check and explore this. I'm going to go ahead and subtract the 6 to the other side, because I have a quadratic, giving me x squared plus x minus 6 equals 0. Again, I could use the quadratic formula if I wanted to, but in this case, very nicely, it does factor into x plus 3 times x minus 2 equals 0. Solving the equation, x plus 3 equals 0. and x minus 2 equals 0. I notice I get x is going to equal negative 3. Now I'm going to double check that before I move on and plug it into the first equation, which is y equals root x, which in this case, y is going to equal the square root of negative 3. And I'm going to stop here. This is not a real number, therefore x is not going to equal. So x does not equal negative 3. It's a good thing I checked. Next up, I'm going to solve the other equation by adding 2 to both sides, and I get x equals positive 2. Plugging that into the first equation, I'm going to get that y is equal to the square root of 2, giving me the ordered pair 2, comma, root 2. Now recall, root 2 is a little under 1.5. So I'm going to go to my graph, and I'm going to notice my graph is pretty close. And I'm going to label my point 2, comma, root 2. For our next example, we're going to use a different method to solve this system. Just like with linear systems of equations, we could use the substitution or the elimination method. We're going to use, in this case, the elimination method. You'll see why in a minute. If you remember with the elimination method, we had to match up the coefficients of either the x's or the y's so that we could add them together, and we would eliminate one or the other. So let's start with this system. X squared plus 2y squared equals 10. And x squared minus y squared is going to equal 1. Now the top equation is an ellipse. The bottom equation is a hyperbola. So I'm going to notice that if I subtract the two, the x squareds disappear as I subtract the two. But before we do that, let's rewrite the ellipse in such a way that it will be easier to graph. So if I divide through by 10, I'm going to end up with x squared over 10 plus y squared over 5, because the 10 and the 2 reduce, equals 1. So let's graph the x, y axes. We'll have to keep a couple things in mind. This one's going to be much more precise than the others. It's a little bit more work. You'll notice on the ellipse, the denominators that I have x squared over 10. That means in the x direction from the origin, I'm going to have to head out the square root of 10. In the y direction from the origin, I'll have to go a distance of root 5. Recall that root 10 is approximately 3.16. You can verify that with your calculator. And root 5 is approximately 2.24. So here we go. as precise as I'm trying to make this graph, it still may not be as accurate as I would want it to be. And that's okay, because in a moment here, after we graph it, we're going to mathematically be able to calculate out exactly where they're going to cross. Next up is the hyperbola. We're going to draw the box. This is called a unit hyperbola, and is used quite a bit in math. Now I'm going to extend the diagonals, just like we learned before. Again, all these dots are not part of the actual graph. This is just setting it up to make it a little bit easier to graph. Notice the y portion of this hyperbola is the negative part. The x portion is the positive. So it's going to go off in the positive x direction. Now these are asymptotes, these dotted lines here. Asymptote is a Greek word that means we're going to get basically closer and closer and closer to it, but we're never going to actually cross it. A lot of asymptotes end up in math. Now what we're looking for at this point are where are these two graphs crossing one another. We may be able to get exact values, and it looks like it's crossing 4 times. So this one's going to be quite the system to solve. So here we go. If I take x squared plus 2y squared equals 10, and I subtract x squared minus y squared equals 1, just remember I'm distributing a negative. The x squareds completely cancel. 2y squared, now notice I get a double negative. A minus y squared gives me a 3y squared. This also gives me 10 minus 1, which is 9. Dividing the 3 out, I get y squared equals 3. Which means that y is equal to plus or minus the square root of 3, which is approximately plus or minus 1.73. Now, when y equals the square root of 3, I plug that in to the hyperbola equation. You can plug it into either. It makes no difference because this point is on both. I get x squared equals the square root of 3 squared equals 1. The square root of 3 squared is just 3. And I'm going to add the 3 to both sides to get me x squared equals 4. Solving this quadratic, I end up x equals plus or minus 2. That gives me 2 points. When x is positive, I get 2 comma square root of 3. When x is negative, I get negative 2 comma square root of 3. On the graph, this is going to give this point here and also the point to the left here. But we're not done yet, because we now need to know what happens when y is equal to the negative square root of 3. Well, again, plugging it into the hyperbola, I end up with x squared minus parenthesis negative radical 3 squared equals 1. Now, order of operations says I have to deal with the exponents first, and a negative number squared gives me a positive 3. Make sure you don't try to cancel out those negatives. Adding the 3 to both sides, I get x squared equals 4, which means x equals plus or minus 2 again. Giving me the 2 points, 2, comma, negative root 3, and negative 2, comma, negative root 3. On the graph, you can see that we have negative 2, negative root 3, as well as negative root 3. And so we have all 4 of our points. Our last example, we're going to say let's solve this using any method, which means we want to choose the most convenient method to use. So far we have substitution or elimination. We're going to start out with x squared plus y squared equals 4, and x plus y equals 3. Note the first equation is a circle of radius 2. The second equation is the equation of a line, which can be rewritten as y equals negative x plus 3. So we're going to try to graph these. So the circle is centered at the origin, and the circle has a radius of 2. The line has a slope of negative 1, which means I'm going to rise 1 and run to the left. And it will have a y-intercept at positive 3. It's possible the line will cross the circle 2 times. It's possible the line will cross the circle exactly 1 time. And it's possible the line will not cross the circle at all. In that case, we'll end up with no solution. And now for the line. This one's going to be close. It looks like it may not cross. It looks like it may cross exactly once. It may cross twice. It's really hard to tell. Right in here, my graph may not be as accurate as I want it to be. So again, mathematically, we're going to have to figure this out. So back to the equations. I'm going to take the circle, and I'm going to substitute for the y, the negative x plus 3. Giving me x squared plus negative x plus 3 squared equals 4. Now there's a rule that we're going to need to use. Let me write it over here in the corner. If I have a plus b, the binomial in parentheses, then I don't just square the a and the b. I end up with a squared plus 2ab plus b squared. Applying that rule, I end up with x squared plus x squared minus 6x plus 9 equals 4. Combining up my like terms, I get 2x squared minus 6x plus 9 equals 4. Sorry, that's a 4 there. It's a quadratic, so I'm going to move the 4 over. And I end up with 2x squared minus 6x plus 5 equals 0. Now here, this quadratic, I can't factor. So I have to go to the quadratic formula. I'm going to notice that a is equal to 2, b is is equal to negative 6, c is equal to 5. In case you forgot, here's the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging my numbers in, negative 6, be extra careful with that b. Double negative going on there. Plus or minus the square root of negative 6 squared minus 4 times 2 times 5. All of that over 2 times 2. Using my order of operations, I'm going to end up with 6 plus or minus the square root of 36 minus 40 all over 4, which equals 6 plus or minus the square root of negative 4 over 4. And I'm going to stop here. This is not real, because we have a negative under the radical. And we don't want to go into complex numbers with the I, because we're actually looking for a physical place where the line and the circle intersect with one another. Because we got a non-real number, the graph is actually quite accurate, and our answer is that there is no solution to this system of equations. And we can use our no solution symbol with a circle with a line through it. And there you have it.